for the time being. That's probably not going to be true in the long term. I think there's a number of interesting detector systems coming online in this sort of burgeoning field of coherent neutrino scattering detectors. And so for the time being, that's the world's smallest neutrino detector. It's also a little bit of a lie. It's an early prototype of the world's smallest neutrino detector, but we didn't want to take the actual detector out of the shielding. That would have been a disaster because it's still taking data. So this is what it looks like. Okay, so I'm going to try and give a little overview of the history of neutrino physics. If you'll permit me to be a little bit irreverent, that's fine with regards to pessimism in the field. I think what we need is a little bit more optimism in terms of how we can do things, and a little bit more willingness to keep trying, and even despite the fact that things are difficult. Okay. It's that big. It's the size of a milk jug. Yeah. It's very small. But there's a smaller one. I'm not going to talk about it. But there's a smaller one coming online. They're taking data in a reactor in South America. They're 100 grams detector, neutrino detector. It's quite amazing. 100-gram neutrino detector. It's a new field, a new era. Okay, so we'll start a little bit at the beginning, if you'll forgive me. Many people in this room, of course, already know all about neutrinos. But you got to start somewhere. And it's really not the story of the neutrino that I'm telling. It's the story of perseverance and doubt, maybe. Maybe that's the right way to say it. So the neutrino was born out of this energy conservation problem in the observed spectra of beta decays, right? So there's this issue with a continuous energy deposition that was observed from these betas, these electrons that were coming from beta decaying nuclei. And it wasn't clear whether or not there was a problem with energy conservation, or if energy should only be conserved in sort of a statistical ensemble sense, or if, as Wolfgang Pauli suggested, maybe there was a new particle that was carrying away some of this energy, and that eventually got coined as the neutrino, right? So in a nuclear beta decay, an electron was emitted, or a beta was emitted, and a neutrino was also emitted. That was very, very tiny, very hard to detect, and very low mass. And he said, Wolfgang Pauli, when he said this, he says, I've done something terrible. I've postulated a particle that cannot be detected. And this is perhaps the last time, maybe, that a theorist had any shame. And I'll give you a couple of examples. And maybe not. Maybe that's not true anymore. But I actually prefer theorists with no shame. So that's fine. And perhaps he shouldn't have said that, because that led to approximately 30 years until something was actually detected. So let's go to a few more. This is Sir Arthur Eddington in the happiest picture you will ever see of him. If you search on Google, maybe he was a happy guy, maybe he wasn't. But I mean, you can sort of see one half of his mouth is turning up. But, everything else is a flat-out frown from him. But his point of view was that also Hans Bethe and Peierls, they also said there is no practically possible way of observing the neutrino. This came about when you actually wrote down, using the Fermi's golden rule, what you would expect the interaction cross-section or the point contact would be. And you said, well, if it's really that low mass and it's not charged, you're not actually going to get it to scatter off anything. You can't detect it. That was the assumption, or that was the realization that they made. And Sir Arthur Eddington is the one who said, so in an ordinary way, I might say that I do not believe in neutrinos. So he's very philosophical on the subject. Dare I say that experimental physicists will not have sufficient ingenuity to make neutrinos. So he didn't think, one, that if you couldn't detect it, it wasn't real. That's an interesting philosophical argument. And two, that there was just, his experimental colleagues just weren't smart enough. Of course, as was later admitted by Reines, this was taken as a challenge. And so in his Nobel lecture, he said, essentially, the reason why he went out to try and observe neutrinos was because everybody said that you couldn't. It couldn't be done. And it took him 30 years to do it, or some 20 years later. But his first idea for how he might do it, which was, living off of the technology developed in the Manhattan Project, he had two options. And the first one that Reines and Cowan decided to go with was they needed to know exactly when these neutrinos were being produced, so they could build the world's most obvious coincidence experiment, which was to take a detector, put it in a hole, and drop it down that hole at the exact moment that a nuclear blast went off. Then you could not possibly mistake your coincidence signal. and any signals in that detector as it was falling down would then be clearly due to neutrinos. This was rejected. They turned it down and eventually decided to do a neutrino experiment with inverse beta decay at the Savannah River reactor by looking for a very characteristic signature of a double bang signature. So they saw the inverse beta decay, which ultimately produced a neutron and then a neutron capture a little while later. And that bang-bang signature was that coincident event that they were actually looking for. It allowed them to separate out signal from their interesting particle physics event from background. So they didn't quite do it this way, but, that would have been awesome. So nowadays, we build cathedrals to neutrino detectors. We have very large experiments. This one is Super K. There's Snow Lab, of course. There's Camland. And now there's going to be Dune. And these things are these giant underground cathedrals where we worship neutrino interactions. And they are really quite amazing and beautiful. And that's because neutrinos are hard to detect. The statement is usually that it takes a light year of lead to stop a single neutrino, or for it to interact at least once, and that is sort of the way of describing how difficult it is to see neutrinos. And that was the sort of standard argument for many, many years, decades. Turns out, though, that it was wrong. So in the mid-70s, with the realization of the neutral weak current, it was realized almost simultaneously by Dan Friedman here, who got his paper out a few months in advance of a couple of colleagues in Russia. And it's actually quite an interesting sort of back and forth between these two papers, if you read them. They realized that, and of course there's always, someone in Russia who's thought of it first, but in this case, it doesn't look like that's true, by about a month. In this case, they realized that there was an analogy that you could make between the way neutrinos might scatter off of nuclei, in particular the nucleons in the nucleus at the time, and how an electron might scatter coherently off of all of the electrons in an atom simultaneously. What that means is there's this coherent scattering phenomenon where the momentum transfer of an electron scattering the momentum transfer is the size of the atom. All of the electrons would recoil in phase, and you get an enhanced cross-section. Friedman realized that there was a similar enhanced cross-section that you could get with neutrinos that might make it possible to observe them, because you can increase this cross-section by increasing the number of nucleons in a nucleus. So what's actually happening here? Suppose you have some incoming neutron, and you have a nucleus that used to live sort of like, suppose it's sitting right there, and you scatter elastically off of it. But its momentum transfer is a z, okay, so it's neutral. It can't be a W. A W will pick out exactly which nucleon it's scattered off of, and then you'll destroy all of the coherence. And so you have this Z. It scatters off of every nucleon according to the weak charge of that nucleon. At the time, they thought that the weak charges were the same between the two. Now we know that the proton has virtually no weak charge. All these nucleons then recoil, and they recoil in phase together because the momentum transfer is of the size of the nucleus. Okay? So they're all basically they're all recoiling together. When you add up the scattering cross-section, you put them in the brackets and you square them, all of this gets squared together, and the cross-section is proportional now, instead of just to the number of nucleons in that nucleus, it's proportional to the square of the number of nucleons in that nucleus. So that's a pretty fast enhancement. Couple of caveats. The initial and final states need to remain the same, otherwise you'll destroy the coherence. So you cannot use you cannot have a Z exchange. That means there's no funny, interesting double bang that you might be able to get, a very characteristic coincidence signature. All you're going to get is this recoiling nucleus that, by the way, because the momentum transfer is so low, is going to be a very low energy recoiling nucleus. That's very hard to detect. There's nothing special about that. It's just a little bump. So you've got to determine somehow what the energy deposited is from that recoiling nucleus. And that's an interesting phenomenon in and of itself, and maybe I'll get back to that later if we have time, how exactly that recoiling nucleus might deposit energy. For the record, some of the cross-sections that I'm going to talk about here today are shown here. The common one, inverse beta decay, that's this solid red one. That's how Reines and Cowan discovered the neutrino. Neutrino electron scattering, that cross-section here is a function of neutrino energy. That's what Super K uses, or at least one of the cross-sections that they use. And then there's a couple others, the most notable being the coherent neutrino scattering off of cesium and iodine right there. And you can see it's orders of magnitude larger. That's how we miniaturize these detectors. We just use a very large cross-section. There are a couple others on lead and iodine, which I'll get to later, but you can see that they're not quite as high, but they're pretty high. And those are important for this experiment and for the broader neutrino program that I'm going to talk about. So, okay, now Dan Friedman says, even in this paper, he says, our suggestion may be an act of hubris because the inevitable constraints of interaction rates, the resolution background, make it impossible to see. And this was in 1974. Many people took this as a challenge. And it's been 43 years since he's made that prediction, and it's been 43 years since this thing has actually been, predicted, that now we've actually observed it. So it's actually longer than the prediction it took to observe the neutrino. So why does this matter? So that's Dan Friedman, again, having a little bit of shame, but maybe when he shouldn't have. So it's actually very interesting. Almost immediately it was realized that this could explain some phenomena that we previously didn't understand. We'll start with supernova. Everybody in this room knows that supernova explode, except when you simulate them, that's how we know they're there. When you simulate them, they don't explode, or at least it's extremely difficult to get them to explode. That's because the process by which a lot of these core collapse supernova proceed emits 99% of its energy in the form of neutrinos. There's not really a lot of energy that's pushing that material out, unless you can find a way to couple those neutrinos that are on their way out to the matter that's in the way. And you can do that by increasing the neutrino nucleus cross-section. So without that coherent neutrino nucleus cross-section, you can't actually get these supernovae to explode. It's a vital part of it. So in a way, supernovae have been measuring coherent neutrino scattering for billions of years. So it's important, and they realize that almost immediately. It's nice to sort of measure this process so we know that this is still true. It's another interesting aspect. This has to do with coherence. The coherent phenomenon is that because the momentum transfer is on the scale of the size of that nucleus, as that scattering loses coherence, so maybe as you go to higher energy neutrinos or higher energy recoils, the phenomenon will lose some of its coherence because you're not seeing all of those neutrons in the farthest reaches of that nucleus. You can study the way in which it loses coherence to understand what's called the neutron skin depth. And so that's interesting in that the neutron skin depth can be directly correlated to the neutron skin depth. The neutron skin depth in a nucleus, there's a relationship that actually correlates that to the neutron skin depth and the equation of state of a neutron star. So if you can really pinpoint that down and measure just those neutrons, not the protons, but really just the neutrons, you can say something about supernova. Or at least that's long been predicted. So people have basically been putting forth these arguments of why it would be very interesting to see coherent neutrino scattering for decades, but without a detector capable of doing it. There's a number of other interesting things. There's a picking from the grab bag of possible physics. There's some beyond the standard model physics where you're looking for different neutral weak bosons, neutral currents that might actually contribute or might be present, but suppressed relative to the one we all know and love with the Z. If they're there, they'll show up in the coherent scattering cross-section. You'll see an enhancement, and it'll be enhanced by Z squared. So you become very sensitive to any extra neutral Z currents. Why is that interesting? Well, they tend to show up in things like supersymmetric extensions to the standard model, that sort of thing. There are some anomalies out there, some more believable than others, with different experiments. In particular, one is the G-2 mu anomaly, sort of explaining that gyromagnetic ratio for muons that doesn't agree with the standard model. Coherent scattering can test that. So it's just one example of ways that we can try to address anomalies that would initially seem completely unconnected to the physics that we're doing with neutrinos. And it can also lead to non-standard neutrino interactions, and I'm going to talk a lot about that near the end of this talk. So how do you actually go about seeing it? Well, about 10 years after it was predicted, a bunch of folks got together, and so Blas Cabrera being one of the first, the only experimentalists on this list. So Blas Cabrera, Larry Krauss, and Frank Wilczek wrote a paper, and then Drucke and Studowski also wrote a paper. And so Leo and Blas are both experimentalists, coming up with ways that you might actually try to measure that very low energy recoil with no other coincident information associated with it. And the idea was to build bolometric detectors. So there's a lot of people here that are very familiar with bolometric detector technology. You're basically just measuring the heat deposited from that recoil. A number of targets were suggested, including spallation targets, reactors, even solar neutrinos, though they completely left out atmospheric neutrinos and the diffuse galactic supernova background, but that's fine, supernova neutrino background. And they suggested they try and do it. And a bunch of people built detectors. This was the progenitor of the CDMS and the CREST dark matter experiments. The problem was they couldn't get the low energy thresholds to see, they couldn't go low enough in recoil threshold to see those neutrino recoils. And so they realized, around that same time, Witten realized that there was a coherent phenomenon in a hypothetical particle that he was talking about in supersymmetry that might explain the dark matter in the universe. And it was the same type of recoil that you would see from a neutrino, and it would also be coherent. And so these experimenters decided, I don't know how that sort of decision is made. It's a realization that at least at the time, it was easier to search for dark matter than it was for neutrinos. And so this is when these experiments basically got started. Nothing against Bloss or Leo, because now they're building detectors to look for coherent neutrino scattering. I mean, it started entire fields this way. It was a wonderful thing. And of course, now we know that we are building exquisite dark matter detectors and really carving out a great deal of phase space. So if this is your putative weakly interacting massive particle mass here on the x-axis, and that's that cross-section that it might have to normal matter, all of this phase space is ruled out. And they're sort of approaching a phenomenon called the neutrino floor, colloquially. And there's a loose definition, but essentially what it is, it's the point at which your detector is going to start seeing the same recoils, but from the neutrino backgrounds, from the sun, from atmospheric neutrinos. And so that's a problem. So we've kind of come full circle on that. It should be nice to know, if we could measure this cross-section, that that's actually there, and it's going to be a real background. So there have been a number of us continuing this effort for probably the last, I want to say 20 years, 15 to 20 years. But we've all been doing it individually, with our own favorite detector technology. Maybe we were an expert in this field, or we thought this was clearly the best, and we went in this direction. And it hasn't been very effective. We don't have the critical mass to actually get something done. Then we had something of a failed boondoggle by the Department of Energy to bring together a bunch of neutrino physicists in Brookhaven and try and figure out what the next set of generation of neutrino experiments is going to be. And it was during the getting ready for that process that a number of us realized that it was time to just combine our efforts to search for coherent neutrino scattering. And so in around 2011, 2012, we formed a proto-collaboration, which eventually we called Coherent, and it doesn't stand for anything, which is what I love most about that name. And so we decided that, one, we were going to form a collaboration. Two, everyone got to deploy their favorite detector, so everybody wins, and we didn't worry about exactly how that was going to work. And three, that we were going to do it at a neutrino source called the Spallation Neutron Source in Oak Ridge, Tennessee. And so this is from a recent collaboration meeting photo. Nowadays we have about 40 people of approximately our 80 member collaboration show up to any given collaboration meeting, and all of our 18 institutions, and approximately the same number of funding agencies. That doesn't mean there's a lot of money, it just means it's crumbs from each one. So we decided to do this at Oak Ridge, Tennessee. So what is the SNS? The Spallation Neutron Source. We call it the Spallation Neutrino Source, but don't tell anyone in basic energy sciences. That really drives them nuts. It's actually a world-class facility. It's a $1 or $2 billion facility built at Oak Ridge to produce these beautiful neutron flux beams that they use for studying neutron science, or the neutron EDM experiment is there. They also use it for material science and understanding magnetism. It's really actually quite exquisite, and it's a wonderful user facility. It also happens to produce a lot of neutrinos. Not as many as a nuclear reactor, but very high energy neutrinos that are pulsed. And it's the brightest such source that exists so far. The spectrum of neutrinos are pretty high. They're about 10 times higher than reactor neutrinos, and reactors give off a lot of neutrinos, let me tell you. Those are bright. But what's particularly cool about this is it pulses every 60 seconds. You get a little proton hitting a mercury target here that lasts for about 300 nanoseconds. That produces neutrinos, because you produce pions, which immediately decay away. That produces neutrinos. Then you produce muons, and those decay away with a characteristic sort of 2.2 microsecond decay, producing neutrinos. And so it's a very interesting pulsed characteristic timing structure that, one, allows us to do a lot of background rejection. So We don't have to be as careful about backgrounds as the dark matter experiments, but we can use the same detectors, or even dirtier detectors, in some cases way dirtier. But also there's some very cute signatures that we can expect to see. In particular, that 2.2 microsecond decay means that whatever you're seeing has to be neutrino related. But the problem is the building, the facility, is designed to produce neutrons, and neutrons produce nuclear recoils, and that is death for a dark matter experiment. Neutrons are the worst thing you could possibly imagine. So essentially everyone was convinced that we would never find a neutron quiet place in that facility. Initial simulations suggested that we would need to build 4 meters of reinforced concrete shielding in a room in every direction just to get rid of all of the neutrons, for instance, that might be bouncing off the sky and coming back down at us. That's quite a lot of shielding. They're very high energy, up to 400 MeV. These are punch-throughs. So we started a very exhaustive campaign of measuring the neutrons in this facility. This is an image of the SNS looking at the target building from a coated aperture Compton scatter camera, where the hot spot is actually where the neutrons are coming from. And you can see that essentially it's very bright. For a moment, we thought about putting a neutron detector on top of that target building, but that was just crazy. So we went everywhere in this facility, starting a very large and exhaustive neutron background campaign until we got lucky one day. Someone was getting a tour of a basement hallway that is used as a tornado shelter, and there was a sump pump down there too, just in case of flooding. And it was where a bunch of barrels of heavy water were being stored from a country that I won't tell you, but it starts with I and ends with N. And the whole hallway was filled with these barrels of heavy water. So they went down there and immediately thought, well, this is reasonable. It's underground. There's a little bit of overburden. Maybe we should bring all of our neutron detectors down there. So we did, and thought they were broken. Immediately, we ran for a week, and we saw no neutrons. No neutrons pulsed coming in with the beam. And so we were convinced that the faculty member who was in charge of this had forgot to plug a cable in, or the high voltage was off, or some such thing. So he went down there, moved it down the hallway, neutrons came back, brought it back, neutrons went away, and we knew we had our place. We had our neutrino alley, and that's what we rechristened it. Of course, there's all kinds of neutron background things going on here, but that's what neutrino alley looks like, or at least that's a diagram from about a year ago of the layout. You can see it's quite long, and all along this area, for most of it, you can actually put a detector. And we do fill it up. In this particular, we've had 9 detectors deployed here. This one has a few. We have the Cesium Iodide detector, which you'll hear all about today. That's located right here at the closest point of approach, first detector deployed. A couple of things we call neutrino cubes. Let's see, a planned sodium iodide measurement and germanium measurement. The sodium iodide is actually there now, and a liquid argon measurement. And so we are actually bringing out all of our favorite detectors and deploying them. And it's very artisanal, and it feels very tabletop physics. I don't mean to misuse the word or insult anyone who does honest-to-God tabletop physics, but we can design a neutrino experiment in 3 months, deploy it in 6, and then upgrade it in another 3. Within a year, we've maybe gone through a couple cycles, and we've been seeing neutrinos the whole time, and maybe we're fixing things. It's quite exciting. So what does Neutrino Alley look like? That means it looks like this. It's relatively constrained. You need to build your neutrino experiment within 40 inches from the wall. You go any further than that, and you start to encroach on the egress path needed for the tornado shelter. But it does mean, because it's so accessible, that it's essentially a place where undergraduates and graduate students thrive, and they deploy all their favorite detectors, including, let's see, is it here? This one is a neutrino detector of sodium iodide built by this undergraduate, who was a Duke undergraduate, who's now a graduate student at Indiana University. And so people can sort of build their own little neutrino detectors and deploy it and see what happens. Especially wonderfully great for students. And we have just a fire hose of data coming at us. This is Grayson Rich, who's one of our more photogenic graduate students, who's actually just finished his PhD, one of the first 2 graduate students from the program, and is now a Kavli fellow at the University of Chicago. So we still needed to measure the neutron backgrounds in that location. We knew that it was still, while they're dramatically suppressed, we needed to do a pretty good job of seeing what they were. And we had a sort of a nice, happy accident. We wanted to deploy that cesium iodide shield, but we needed the new cesium iodide crystal. This shielding and system with detector needed to go in this location. But the detector was stuck in the Ukraine behind a war, some sort of hot war, whatever the conflict that was going on there at the time was called. It was sitting in a warehouse where no one from the company could physically go get it. But we had the shielding, so we decided let's deploy the shielding and put a neutron detector in there and use this time to sort of measure what the neutron backgrounds would be in situ, right in there. Because neutrons will scatter off your nucleus, give you a little nuclear recoil, mimic your signal, and it could be a problem. So we did that, and we were able to constrain the neutron backgrounds with that liquid scintillator cell so that we can now use that and propagate that forward to understand our backgrounds when the cesium iodide was relocated in there. So that was particularly useful. So that's not the only thing it measures, though, because there's a relatively interesting background that we realized in one car ride from Durham out to Oak Ridge, Tennessee, and this was actually a realization of Grayson Rich, the aforementioned Grayson Rich. By the way, these are the aforementioned heavy water barrels from that country that I won't say who they're from. And he realized that there's a neutrino interaction on lead, which is really important for our process nucleosynthesis, for how heavy elements are created in the nucleus, in the universe, and in the stellar environments, where you have neutrinos that can interact on lead, especially electron neutrinos, undergo a charge current reaction and emit 1, 2, or 3 neutrons. And the more neutrons that are around help the R process, right? Well, he realized that this was a problem for us, a potential background. These high-energy neutrons would hit the lead shielding that this detector was built out of, that you see right there, produce the neutrons. Those neutrons would then straggle into your detector, and they would arrive producing a low-energy signal that looked like a coherent neutrino scattering signal and come in time with the exact same timing structure that we expect from neutrinos. So they would even share that 2.2 microsecond decay. And so we decided that we were going to use the same data set to try and constrain what that was. With just the neutron detector in there, we could constrain what that cross-section was. It had never been measured before. There's only a handful of neutrino cross-sections that have been measured in this energy. So we decided to go after that. Yes? In this particular case, it's a charge current reaction. So it's a single nucleon. It converts a single... Yeah. So in this particular case, we don't. There's a W exchange. There's a charge exchange reaction, and this is allowed to happen, but it's suppressed. Okay. So the other case, no charge exchange reaction is allowed to happen. It can be the same wavelength neutrino, but the only thing you'll be able to observe is that kick of the whole nucleus moving in as one. This one's easier to see because you see a lepton, and then you might see some de-excitation gammas, and then you see a neutron or a couple neutrons coming around. We only looked for the neutron. And so what did we see? We looked for the timing structure of these neutrons. Of course, there was a steady state background. This is the time difference between when there was a beam pulse and when the neutron arrived in our detector. So there's a steady state background of neutrons sort of arriving in the detector. There's a giant pulse from the protons on target, from the actual neutrons that we're worried about. But it turns out it's small enough that we don't have to worry about it. But that's what that big peak is there. That's the one that's the neutrons we were originally really terrified of. Very small, don't have to worry about it. Results in like 2 or 3 counts in the final fit. And a little extra little thing there that fits out with a significance of about 2.7 sigma, 2.9 sigma, for something that's happening from this charge current reaction from this delayed neutrino, this one that follows that 2.2 microsecond decay. Those were the electron neutrinos follow that signature. And so while this dotted line here is the expected theoretical expectation, sort of what we expect from theory. What we know is that the cross-section of neutrinos on this lead is about a factor of 1.7 less than what theory predicts. But that's okay, because theoretical predictions have been all over the map, like 300 factors of 3 differences. So it's actually potentially useful for theorists. The other thing we know is that it's also not a problem for our experiment, and so we move forward. We're still measuring this with other means right now from the nuclear physics angle. We're interested in the ratio of 1n to 2n, what nuclear states are populated, all that sort of stuff. And we're doing it with other nuclei. But for our experiment moving forward, in this shield, we know it's not a problem. Neither of these sets of neutrons are a problem for us. No, it's one neutrino with one nucleon converts it. Then you're in an excited state of bismuth. Okay. They're, no, they're all the same energy neutrinos. That's right. Yeah. Hmm. It is the same energy neutrinos, right? But in one case, you just have a different. Okay. I would be happy to. Yeah. No, it is the same energy neutrinos, and it's a particular interest for the high energy neutrinos we see at the SNS because you're above the neutron separation threshold. So the energy that you can dip to the nucleus is above 10 MeV or so, 9 MeV. Not a problem for reactor neutrinos because you would never be able to give enough energy to the nucleus of the lead shielding to produce this neutrino. So it's one of those things that we in particular had to worry about. Oops. In this case, you end up with enough energy in the excited state that it's sort of that anywhere between 1 or 2 neutrons. That I couldn't tell you. Yeah. 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 So John Engel, who's at UNC, has a really nice, thorough paper on this. It differs, so does Langaka and Volpe. And so there are some differences in some of the cross-sections estimated there, but of course they come from the different nuclear models. I'm sure it's much more complicated than how I'm explaining it, because I am probably the world's worst salesman when it comes to nuclear physics. So okay, but the important thing is here, it's not a problem for us. So having discovered that, we move to deploying the cesium iodide detector, and that's what you see here coming back to this picture. That's the actual true world's smallest neutrino detector for the time being. It's 14.6 kilograms. It's just cesium and iodine, but they're very close to each other, right, in terms of mass, so we treat them as if they're basically the same in terms of the cross-section. I mean, we don't, but they can be. And then we wait. You can see sort of the timeline of the experiment here. This is where we first started deploying detectors, measuring neutron backgrounds. This was that deployment of that shield with measuring the process that we were just talking about here in late 2014. And our first deployment of cesium iodide is this thick red line that we see here. It's been accumulating protons on target since. Since we have been running, the SNS has accumulated something like 6 times 10 to the 23 protons on target. There's more target here, which is, as everybody knows, it's very close to 1 mole. It's about 1 gram of protons. Compare that to the neutrinos that are produced, for instance, at Fermilab, and you're talking about protons on target at the level of 10 to the 20. So 3 orders of magnitude difference. We have since also deployed a number of other detectors here, and in the most recent plots, we have another 2 detectors that have come online. So there's a lot of data coming in, and then we have to try to understand all of it. But let's get back to cesium iodide. What do those signals look like? Even though it's a higher energy neutrino, it does give a very low energy nuclear recoil. So you would expect from cesium or iodine nuclear recoils of the order of 10 to 30 keV. Compare that to some of the lighter targets that we're building, in this case sodium recoils in sodium iodide, liquid argon, or germanium. So some of the lighter targets are going to be easier to see. Cesium iodide had the highest cross-section, but possibly the most difficult for us to see from the point of view of terrestrial. What does it look like? Well, these nuclear recoils deposit energy. They sort of produce an electronic excitation in this crystal lattice and then result in scintillation. We end up seeing about 1.2 photoelectrons per keV of nuclear recoil after accounting for something called nuclear quenching or quenching factor. It's a single channel detector. Okay, so this is a neutrino experiment with 1 channel. Relatively simple. And this is the waveform of the charge that's been accumulated at the end of a phototube that's measuring that scintillation. And we show here the protons on target. That's the arrival of that event. This is a candidate event from scintillation produced from a candidate neutrino with the scintillation decaying away with the characteristic time of scintillation that you expect in cesium iodide sodium doped. And so we measure that. We integrate that. And we also compare that to a background region just before that so we know what the differences are. We expect about 5 to 10 to 30 photoelectrons. 30 is optimistic. It's at the highest end. I don't know if we've yet had a candidate event that's at 30 photoelectrons. But so I mentioned something there very briefly, and it's pretty important for understanding these results. And it's something that we call in the field called quenching factor, but it's really fundamentally just a different yield or the different number of quanta that are produced when you compare an energy deposited from a nuclear recoil as compared to energy deposited from an electron. So in this process, you have a nucleus that ultimately is charged. It recoils, it leaves behind a couple of its valence electrons, collides with a number of other nuclei, and produces a phenomenon that's called Coulomb Explosion. Okay? That's a very electromagnetic phenomenon, and so it excites modes in that crystal lattice and produces scintillation. But it does it in a completely different way than if an electron had actually passed through that same material. And it actually produces less scintillation, of order of 15% of the scintillation you would expect from a similar energy recoil from an electron. So now we're talking about a low energy nuclear recoil that's 7 times harder to observe. And that has to be measured very, very carefully in order to interpret any of the physics. And so we do that at the tandem accelerator at Tunnel's, the lab at the Trigo University Nuclear Lab at Duke campus. We produce beams of neutrons from the lithium-7 PN process. We collimate these neutrons. We shoot them at detectors of interest. They're monoenergetic neutrons that we can tune to all kinds of energies. And we scatter them into a range of what we call backing detectors, that when we see a coincident event in a backing detector, we know that we've kinematically constrained that event, and we know exactly how much energy is deposited in that recoil, and we can calibrate it. And we're not after sort of proof of life calibrations, like, oh, I know I see something, therefore I'm sensitive. We're after precision measurements of these calibrations. And we're doing this, we have a large program that we're doing this for all of our detectors for Coherent. And this particular one was a sodium iodide calibration, but we've done this for cesium iodide as well. In particular, so some of our results, just for comparison, sodium iodide calibration here, you see in blue points here with very nice error bars on the background of sort of the contemporary literature before our measurement. So what we're really after is those precision measurements of the quenching factor, the percentage of the energy that you observe in the channel that you're measuring as a function of your recoil energy. We have to do this, we have to do better than this, actually, ultimately, for all of our detectors. That's a problem for cesium iodide. So cesium iodide had a similar sort of global dispersion of measurements for the quenching factor. We knew this. My colleague and former advisor, Juan Collar at the University of Chicago, and I decided we're going to measure this. We have to be systematic about it. We have to sort of take a double-blind approach to it. We're not going to influence each other. We do 2 measurements, both with the same crystal, both at Tunnel, different beams at Tunnel, but completely different systematic setups. And we measure 2 sets of data. These red points were produced by Chicago at Tunnel, and these blue points were produced by the Duke graduate students at Tunnel. And while I can say now we are resolving that difference, and we sort of know what this comes down to, it's really subtle effects in how you understand what a single photon is and how it's measured. At the time, we decided that we didn't know how to interpret this, and so we took the mean value of those data points and all of the world's data points up to that point, and took the spread as the uncertainty around that mean value for what this quenching factor should be. The reason we need to know this is we need to predict what we're going to see in the detector, and this is what we took. It's a very large uncertainty. More measurements have been performed and reanalyses have been performed by different students and by a third party, and I think we know what's going on, and we have a publication coming out this year on that. So our largest source of uncertainty will be, hopefully by the summer, be gone. So what did we ultimately see? Going back to the actual neutrino experiment. After we predict this signature, understanding what the standard model physics process might be, understanding what the quenching factor might be, and turning into photoelectrons, we can plot that on a graph here, which is number of photoelectrons here on the x-axis versus the expected number of counts for how long we run. And we compare that to the data that we observe. This is background subtracted, but this is what we observe. We see the green data point, the green sort of histogram here. Those are the expected number of neutrinos from the standard model with no fit. There are no floating parameters in here. That's a straight out of the box calculation. That little sliver of orange up there that you see there, and where it's all sitting in the prompt window and the arrival time window. So the x-axis here is the time of arrival after the proton's on target pulse. You can see that the neutrinos have that nice 2.2 microsecond characteristic decay with a little bit of the prompt neutrons contaminating things there. That is nice because it tells us really that those prompt neutrons aren't going to be a background for this experiment. And it lands pretty much right on top of the data. This result, there's a more sophisticated statistical analysis that I'll get to in a second, but this result produced what was eventually a 6.7 sigma evidence for the observation of coherent neutrino scattering. It showed up on the cover of Science, which was an interesting story in and of itself, how that happened. And then we got a nice little kudos at the end of the year where we got like second place in the Breakthrough of the Year award for Science magazine. We didn't beat out, what's the one? It had to do with immunocancer therapies for little children, which I don't think we had a chance with anyway. I think we weren't going to beat that one. But we did beat out the, amazingly, we don't know how this happened, we did beat out the neutron star merger, which should not have happened either. That was clearly a much more interesting result than what we had to say, but whatever. Popular science is what it is. So how did we actually analyze this in a more sophisticated way? We used a two-dimensional maximum likelihood analysis where we accounted for the expected energy and energy and timing distribution of the neutrons, which you can see there. So they actually have a high energy tail, but they all arrive in the prompt window. And compare that to the neutrinos, which you actually see here, which are slightly lower energy and they can have some delayed time component. So we have this three PDF fit. I say 3 because these 3 neutrino PDFs here are what go into this fourth one right here. And we fit it, and we end up with a result that observes of the order of 130 counts, consistent with a coherent neutrino scattering. We call it sevens, by the way, coherent elastic neutrino nucleus scattering, and rejects the null hypothesis at close to 6.7 sigma. It's important to note that we had 2 parallel analyses that were not talking to each other. Communication went through their advisors and then through me, and no communication went anyway except sort of arranging times and schedules and knowing when we needed to write the paper. And they both came up with similar results, and both of them were presented in the paper. The uncertainties are completely dominated. These are the systematic uncertainties by the quenching factor. So about 25% uncertainty on the predicted rate due to not really understanding the quenching factor. So clearly we have to do better on that. And that's where a lot of the meat and the physics is going to come in the future. This vertical band here is that standard model prediction, and the gray band is the uncertainty on that standard model prediction, and this is our best fit down there. So we came within 1 sigma of the standard model prediction, but we'd like to do a lot better. Okay, so we saw it. That's awesome. But the whole gig was all about all the cool physics you could do in testing the standard model after you observe it. And so the lowest hanging fruit that we had that we could do was to just count the rate and compare that 130 events to the standard model prediction of about 170. And what does that say about other types of neutrino interactions, what are called non-standard neutrino interactions? These are little epsilon parameters or perturbations on the cross-section of the neutrino with, say, neutrons or protons, or actually up and down quarks for the electron-type neutrinos. And the allowed region that was not previously ruled out by other experiments, in particular the CHARM experiment, which was an experiment in the 80s that sort of lingered until about the early 90s, was in that was the allowed region there in that gray area. Our result, just out of the box without doing much except counting numbers, was able to produce a simple band here that sort of said, well, we've been able to reject everything outside of this purple band now. And so we had a pretty dramatic, with probably the worst counting experiment you could ever imagine, looking at 130 events versus 170, we dramatically improved sort of the existing allowed space for something called non-standard neutrino interactions. Now, it gets a lot more complicated than this, and there's a lot of people in this room that do the non-standard neutrino interactions that take into account all kinds of parameters. And it's really interesting stuff, but I don't exactly have tons of time to talk about it. I'll see if I can talk about it a little bit. So one of the first results that came out analyzing this was a rejection of something that was called the large mixing angle dark solution for neutrino oscillations. And this was a potential problem for an experiment like the upcoming DUNE experiment. It's a $2 billion experiment to look for CP violation in neutrino sector and a couple of other things. But it would have been potentially impossible if non-standard neutrino interactions were allowed, and one of the possible solutions was in this dark solution. It would have been impossible for Dune to measure CP violation in their experiment if this were true. So we were informed that, in fact, we had just shown that that was no longer an issue after our result. So that's a nice little thing. Other results find tension by looking at the change in the possible recoil shape. So these are like shape deformations because of kinematic terms. Potentially you have some new mediator that's very light, that is a dark mediator that might change the shape, the way in which the signal would show up, maybe interference terms. And you can rule out, at least to something like 2 sigma, a potential candidate for the G-2 mu anomaly. So this candidate of what's called a dark Z mediator, or Z prime, which could possibly explain this other anomaly in high-energy particle physics, is living here, and our result sort of rules it out, finds tension with it at close to 2 sigma. But, I mean, these are other people's results. It's very interesting stuff. I mean, it includes other results too. First attempts at trying to understand what the neutron radius would be. That wasn't quite all that exciting. More interesting results that are actually centered here are when you take the full spectrum of possible non-standard neutrino interactions into account. What can you say about that parameter space? And you can see our sort of little silly parameter space is living over here. That's what we drew, but it's actually much more complicated than that. Very meaty, interesting physics. And as other detectors come online, with different numbers of up and down quarks, all kinds of very interesting things can come can actually go into this. So where do we go from here? We have many detectors, and they're all coming online, and so far they all seem to be going well. The Cesium iodide detector you see here is a threshold of about 6.5 keV. There are a number of germanium detectors coming online in what we think are going to be 2 phases. They're going to be sitting right there. The first phase is going to be sitting right next to the Cesium iodide detector. The liquid argon detector, which is an honest-to-God liquid argon detector that operates just like the dark side experiment, is sitting in its cryostat, in its shielding, and running and undergoing calibrations down the hall here, and that's very exciting. And that's actually quite a complicated thing to get running in a hallway that's used for a tornado shelter. It dumps quite a bit of heat into the hallway. When we originally turned it on, the whole hallway heated up, and all of our digitizers shut down because they were too hot. And so we had to retrofit the hallway so we got better air handling in there, and then we'd pump the heat out through a water cooling unit. So some of it actually is honest-to-God infrastructure building, but, you know, a lot of it's tabletop stuff. And then sodium iodide detectors we have coming online. We have already deployed a 185 kilogram sodium iodide detector, and we're going to conservatively to 2 tons, though I think it'll probably more end up in the realm of 7 tons based on what will fit there in that hallway. The 185 has been operating for now 9 months, I think, and the final designs and construction of the multi-ton detector are happening as we speak. So that liquid argon experiment looks. This is what it looks like. So of course we're going to see some nice recoils there. That's its lead shielding. It's a lot easier to build an experiment in your lab, especially with liquid argon or some cryogenics like that, because you can make decisions that don't rely on absolutely crazy estimates of safety concerns. But at a national lab, you have to, in Oak Ridge, Tennessee, you apparently have to really worry about the possibility that an earthquake's going to come along. And so you have to build in a lot of infrastructure to make sure that your lead does not topple over in case you have a very powerful 7.5, earthquake happen. But, fine, that's fair. Particularly interesting there is argon 40 is even. So a lot of the theoretical uncertainty that goes into coherent neutrino scattering cross-section goes away. Now, that being said, I want to emphasize that the reason why coherent scattering is so useful for studying new physics is because it is one of the 2 best predicted neutrino cross-sections. It only has an uncertainty of the order of 0.2 to 0.5%. The other one being inverse beta decay. Everything else, all other high-energy cross-sections can have uncertainties of the order of 30% or more, hundreds of percent. The germanium detectors are coming online. I should say they're being tested at Duke right now, and then another set are being designed at Chicago. They have very low thresholds and exquisite energy resolution, so they're going to be great for studying nuclear form factors and looking for deformations of the shape and Z prime mediators. The energy resolution we would be talking about, thresholds would be of the order of 200 keV, 200 eV electron equivalent, and resolutions that are of the order of about 50 electron volts. So that's very nice, and so this is a PPC detector. Then there's the sodium iodide detectors. The 185 kilogram array I told you about, that was an undergraduate senior thesis project. It's really designed aside from studying what the backgrounds are for this particular type of experiment, for a coherent scattering experiment, it's really designed to look at another neutrino interaction. In this particular case, the charge current interaction on iodine 127. Why is it interesting? It's only been measured once before, one of the few, by the LSND experiment, actually the pre-LSND days. That cross-section has a very large theoretical uncertainty. It's about 40% theoretical uncertainty. The previous measurement is coincidentally about 38% uncertain. And the interesting thing here is that 40% is almost due entirely to G sub A quenching. That uncertainty. What is the value of G sub A? And why is that interesting? Well, it's a particularly important input to trying to understand what could G sub A be in neutrinoless double beta decay experiments. It's another set of experiments in low background physics where you're trying to actually go after whether or not the neutrino is its own antiparticle and whether or not there's lepton number violation in the universe. That experiment is operating and taking data. We have neutrinos in the can, and we hope to publish soon as well. We'll see how things go. The multi-ton array, as I said many times, is actually is going to be coming soon as well. And then we have other detectors that we say that they're part of incoherent. There's coherent and then there's incoherent, meaning that they're not actually benefiting from this enhanced cross-section. In particular, we have specifically a bespoke designed experiment just to look for this neutrino-induced cross-section on lead that results in neutrons, with the hope that you can measure the ratio of single to two neutrons. And if not, maybe we can possibly investigate all kinds of really interesting physics that's in there. And then a mirror experiment that does the same thing in iron. And when these are done, we'll swap them out for copper and who knows what else. We have a lot of other material lying around that might be very interesting. Some of these are important for our process nucleosynthesis, and others are important for both nuclear structure and supernova shock revival. Trying to understand how in core collapse supernova, how the neutrinos interact with that iron when the iron is really the only thing in that core. It's particularly important. And so these are sort of side projects, but they're also important for understanding backgrounds that we might observe in our detectors. Okay, so that was a lot. Okay, and I know that some of you lost me on like slide 4. So where do we go from here? Lots more exposure for cesium iodide. A lot of more detectors being turned on, and as I said, a fire hose of data coming at us. But really what makes this interesting is that we finally have that neutrino facility that we've been wanting for a very long time that can be used to study both high energy physics questions and nuclear physics questions. Can we use this to look at double differential cross-sections of neutrino scattering on interesting targets like iron that can tell us something about nuclear structure, or tin, or tantalum? And can we actually look for other processes that are be interesting in stellar environments? And then, of course, there's a ton of new detectors coming on that are looking for coherent neutrino scattering. Well, there are grams and hundreds of grams of new detectors. The Connie experiment I explained. The MITRE experiment, which is a local experiment here. There's the CONUS experiment, which is it's a daughter experiment of that first CREST experiment that I told you about. It's at TUM in Munich. And so this is a bolometric detector with sort of sapphire or something very close to it. The RED detector, which is a Russian detector. And it's a liquid xenon target, so it's going to test what this background will be in explicitly liquid xenon dark matter experiments, this neutrino-induced background. And then Nucleus, which is a germanium experiment that's happening at the Brokdorf reactor in Germany, and Ricochet, which is a similar experiment to MINOR and comes also out of the CDMS collaboration. So I know I've talked about a lot, but I'd like to thank you for your patience and for spending the time to come here and listen to some very cool, potentially new facility and new results that are going to be coming your way. Thanks. Oh, no. I think that is clearly the one that should have won. In fact, the editors agreed with us. Yeah. No, the editors certainly chose that for a reason. So, so the energy spectra, let's see if we can go back here fast enough, is of the order of, the average energy is about 30 MeV. There we go. So most of it is from the Michel spectrum, right? So these are less than 50, average energy around 30 MeV. There's some higher energy stuff because this is a proton beam, right? MeV proton beam, decay in flight neutrinos, but they're suppressed by orders of magnitude, so that we don't really see any of those. It's really, yeah, all of those neutrinos that are, yeah. And of course, if it's a forward scatter, it's going to be more coherent because the momentum transfer is less. Yeah. So these particular neutrinos are of the order of, I can tell you, so we start to lose coherence in the cesium iodide. So I can tell you just from empirically, it's of the order of the size of the nucleus. So it's about 5. Oh, actually, I could probably tell you. It's about 5 Fermi, I think, right? Is that? So let's see here. So people have tried to interpret our result and fit it, which I actually think is a little bit misguided, to try and understand what the neutron skin depth is here. They get 0.7 plus or minus 0.19 or something like that. So we're not there yet. We don't have the statistics or the uncertainty on the quenching factor. But this is something we're aiming for with the germanium detectors. We hope to be able to do something important in this realm there. Oh, yeah. Why do you think it's in the extra slides? So the question was, can I elaborate a little bit more on the systematic difference in the quenching factors between me and my former advisor? Let me tell you, I enjoy telling him he's wrong all the time, but I don't know that I want to pick a side here. The fundamental difference comes down to how you define quenching factor. And whether or not you're talking about an effective quenching factor or a true quenching factor, and how this was actually located into the actual results. There's also a possible effect of some analysis filters that were applied to the waveform to get rid of noise that could have potentially a nonlinear effect, and we're starting to understand what the impact of those things were after the fact. And what it really is, it's not any one thing. It looks like it's a sum of a number of very small things. Well, the 25% is related to this difference here. It's the quenching factor is 8% of what you would expect, and that has a relative difference of about 10 or 20. That's got a 10 to 15% error. That 10 to 15% error on that quenching factor correlates into a 25% uncertainty on the predicted rate. Oh, I don't know if I want to go up against Janet Conrad. So don't put me on the record on anything about that. So the Deadlifts Experiment is a proposed neutrino source that I can't remember. There's been a number of different incarnations, but the idea would be to produce neutrinos potentially underground near a neutrino detector and measure of the order of 10-ish MeV neutrinos. I think it's a higher flux than this. And it would be underground, which we're not really underground, and look for sterile neutrino oscillations. One thing I didn't talk about is that coherent neutrino scattering is a very interesting tool to look for sterile neutrino oscillations, because it's a neutral current process, and only a neutral current process. So if neutrinos oscillate into a different flavor, the sterile, we will see that. That being said, it's hard enough to deploy one detector right now. It'd be nice to be able to put a lot more detectors in play to do that. But it's not like we don't have that sort of stuff in mind. I don't know if you can see here, but almost all of our detectors are on pallets. So they're all movable. So in the back of our mind, we're always thinking about this. But we're not there yet, especially considering that we share funding at Oak Ridge with the Prospect experiment, which is also a sterile neutrino experiment. So should something be discovered in the way we like to say it is, should something be discovered in the neutrino sector, in the sterile neutrino sector, this would be a really neat way to come in and help answer questions after the fact. Oh, the quenching factor drives all of the uncertainty on the prediction. Yeah. That's right. Yeah. Uncertainties on the form factor. So there's a bunch of different models, especially for heavy nuclei. They contribute to something like 5%. If we were to just take the selection of form factors and sort of test them, it's a 5% uncertainty. One thing you might try to do is to say maybe take a bunch of skirm models. This is something that Gail McLaughlin has done at NC State. turn those into an effective form factor and sort of try and measure it. It'd be very interesting, but I think right now we're still dominated by the uncertainty from the quenching factor. That shape is what's dominating everything. Yeah, this is where germanium is going to do an amazing job because we really have, we're measuring quenching factors in germanium. Let's see if I can find it. Here we go. And it's pretty well modeled and well understood relative to cesium iodide. There's a lot more data than this too. And we're actually measuring, looking for channeling effects or directional effects right now at tandem. The idea being that when germanium turns on, this is the detector that needs to have the most precise, well understood response. Yeah. Most of our recoils are going to be sort of in this regime right here at the SNS. If you go to a reactor, they're all down here. Yeah. So I'll talk about it from the point of view of a germanium detector. So 30 years ago, Paul Luke, there was this possible explanation for the solar neutrino problem, which was called the cosmion. And there's a new dark matter particle that the sun might have been emitting. And you might be able to look for it with low energy recoils in germanium detectors that were right about then being built to search for dark matter. But you needed a very low threshold. Paul Luke, who was at Berkeley at the time and really a germanium detector expert, decided that, well, you could do this with, at the time, a state-of-the-art FET to measure the charge that's being collected on that electrode. That state-of-the-art FET was the quality of which was driven by industry. What does the military need? What does industry need to be able to measure these very small charge signals in, say, radio signals, that sort of thing? And so it wasn't so great. And it turns out it looked like he couldn't actually search for the cosmion, so he sort of gave up. He had other things to do, too, many more important things to do. 20 years later, when we developed the PPC, which is one of the types of detectors that we're planning on developing now, so that was in 2005, we benefited from 20 years of work and a factor of 20 improvement in the noise in that FET, just from industry. That's for charge collection. Some of these other detectors, they measure light. What do you have to do to see that in a very sensitive way? You have to build really nice light detectors that are very low background and very low dark counts. That also simultaneously don't give off so much radioactivity that they basically illuminate your entire detector. And so they have to be made out of low background quartz and low background parts and move very far away. And so fundamentally, okay, it's very complicated, but fundamentally what we've basically done is benefited from all of the work of the dark matter community in developing all these low thresholds over the last, say, 30 years, 40 years, 30 years really. And then the SNS turned on at the right time, and we got the political will to start deploying these things there. So it's just this steady drumbeat of detector development, right? I mean, it's very complicated. I mean, so the stuff with the super CDMS style detectors, the Paul Luke effects. This is the same Paul that in 1985, 1987 tried to search for the cosmion. Came up with an idea to decrease the threshold in sort of these bolometric detectors, and it's a very interesting idea, and it could be used also to search for coherent neutrino scattering. So clever ideas, steady work, don't giving up. I guess that's the pedantic way of saying it. I hate to tell you. Currently, this detector here is about twice the lowest. This detector that we're testing with right now at the tandem has a about 190 electron volt threshold, and that is about 50% more, close to twice more, 2 times the noise that Juan has for a detector that's in his possession right now at Ohio State, and he's going to be shipping it out to Tunnel for us to measure it as well. Electron equivalent, that's right. So you multiply it by about 6 to get the nuclear recoil threshold. So just steady development. I mean, even in the last 10 years, we've seen a pretty dramatic, factor of 2.5 reduction in threshold in just PPC detectors. Learning how to. Here's a good example. The FETs changed a little bit, but the largest noise was a leakage current across the surface of that PPC. Let me see if I can find that. Oh no. Well, here we go. So the largest. So if we can find the surface of that PPC here. And this is something that the CDMS folks in the room would appreciate. So that's your germanium detector. It's actually a broken one. And that's your point contact. That's the electrode. And you put high voltage across there. So the folks in this room probably used to putting like 3 volts, 10 volts across it. That's your high voltage runs. Oh, okay. That's not bad. So this you have to put close to 5,000 volts across that. And you're going to be dragging current across that surface. How do you suppress leakage currents across that surface? It's a material science issue. And so that's actually, that leakage current drives the noise to a large extent. Capacitance does too, but mostly that leakage current right now. Yeah. No, it's not at all. If you talk to the experts on this, it's very much an artisanal process. It's like if Mercury is in retrograde, you're going to have to build the whole detector all over again. Like, they don't really know. They kind of know, but one of the reasons why the detectors are so expensive is that it's a little bit of a trial and error process. So they'll build a detector and they'll test it, and if it doesn't have the noise, they start over. They dunk it in hydrochloric acid and start all over. And so a perfect example of that would be the FETs. The FETs are as expensive as they are because they'll make 100 for every one they sell, and the other 99 have been tested and they throw them out. Yeah. And so, I mean, some of these things, not very efficient, but they're very low noise. So. Oh yeah, that's wonderful. Yeah, yeah. So this would be with the mini PPC that Paul had at Berkeley. Yeah. I think it was like 40 30 or 40 Kelvin, or even lower. Oh, nice. Yeah, very exciting. Yeah, 30 millikelvin. Oh, wow. Okay. So all of that is all interesting, very in the weeds detector stuff. But basically, it's you don't know what you're going to run into from the point of view of backgrounds or threshold, and you just have to, when you run into it, deal with it, and it can take some time. Try to understand it. Oh, thank you.